This tape presentation is going to deal specifically with the 1B and 2B range of carburetors and follows on from part 1, which dealt with the 6 stages of carburation. It's therefore important that you should have viewed part 1 before commencing this session. Don't forget to refer to the workbook when requested. Let us firstly remind ourselves of the 6 stages of carburation. 1. Choke. 2. Idle. 3. Progression. 4. Acceleration. 5. Main system. 6. Full load enrichment. We'll take each of these stages in turn to see how they apply to these specific carburetors and look at any adjustment criteria. But firstly, let us identify the 1B and 2B models. The 1B is a single-stage downdraft carburetor. There are 2 basic versions of the 1B, which was first introduced into the UK on the Passat and Audi 80 in 1979. The 1B1, which has a manual choke, and the 1B3, which has an automatic choke. The 2B carburetors all have automatic chokes. The 2B2 was first introduced into the UK on the Sirocco in 1974. As time goes on and further improvements are made, the last digit will change. That is 1B4, 1B5, 2B6, 2B7, and so on. If the carburetor manufacturer needs to modify the carburetor to suit the vehicle manufacturer's requirements, then a modification state number is stamped onto the carburetor body. For example, 2B5 AU113. Now stop the tape and refer to the workbook. Let us now work through the 6 stages of carburation on the 1B and 2B, starting with Stage 1, the choke. A cold engine requires a greater volume of air and fuel mixture, a slightly richer fuel-to-air ratio, and a faster idling speed. And it is the choke assembly operation which meets these requirements. The choke mechanisms on both the 1B and 2B work in the same way. As the engine cools down, the automatic choke's bimetallic spring gradually tensions up, ready for the next time the engine is started. The maximum amount of tension is only applied when the engine is stone cold and the ambient temperature is low. The bimetallic spring tension is released by the driver pushing the accelerator down once before starting the engine. The tension then closes the choke valve. The effect of closing the choke was shown in part 1, the basic principles of carburation. As soon as the engine is started, 2 things happen. Firstly, an ignition-fed electric heater starts to warm the bimetallic spring, thereby gradually relaxing the tension. The tension is fully released after approximately 4 minutes, depending upon the ambient temperature and the speed of the engine warm-up. Secondly, a choke pull-down diaphragm pulls the choke valve open to a set gap within a second of starting. Then, after a delay of 4 to 6 seconds, the pull-down unit pulls the choke valve open to a larger second gap. The delay is caused by the green depression reservoir on the offside front inner wing. The choke valve gaps are adjustable and are crucial for obtaining good cold running characteristics without stalling. Too wide a gap will give a weak mixture and the engine will have flat spots and may stall. Too narrow a gap will give a rich mixture and the engine will choke up and stall and the fuel consumption will be high. An extra item to the choke system on the 1B range is the cold starting enrichment. This only operates when the engine is cold enough for the tension of the choke bimetallic spring to fully close the choke valve. In this position, this hole in the choke valve is close enough to the end of the full load enrichment tube to create a depression at the end of the tube. This causes extra neat fuel to be drawn into the engine for cold starting enrichment. As soon as the engine fires and the choke pull-down diaphragm pulls the choke valve open, the enrichment stops. Adjustment of the choke bimetallic spring tension. Before adjusting the tension, it's important to ensure that the correct choke assembly is fitted, as each carburetor version has a choke bimetallic spring of slightly different operating characteristics. These are identified by the number stamped on the choke cover. Refer to the workshop manual for the particular vehicle. If the number is correct, the tension can be adjusted by aligning within the marks on the carburetor body and choke cover. Adjustments of the choke pull-down diaphragm for the choke valve gaps. There are two versions, small and large. The adjustment procedure is the same for both versions, but only the larger choke valve gap is adjustable on the older small unit. With the new larger unit, both gaps are adjustable. It's recommended that if you have a vehicle with cold running problems, replace the small unit with a larger one. This will enable you to obtain very accurate adjustments. The adjustments are carried out as follows. 1. Remove the outer hose from the pull-down unit, the one which goes to the green reservoir. 2. Remove the inner hose from the pull-down unit and carburetor and check that there is a restrictor in the hose or in the inner connection of the pull-down unit. 3. Refit the restricted hose to the inner connection of the pull-down unit only. Connect the VAG 1390 vacuum pump to the other end of the hose. 4. Open the throttle, close the choke valve, then close the throttle. Ensure that the fast idle screw is on the highest step of the cam. 5. Operate VAG 1390 continuously. The choke valve should open to the first gap. Measure with a round feeler at the lower edge of the choke valve and adjust if necessary by moving the pull-down unit's end cap with a 6mm Allen key. Large unit only. 6. Close off the outer connection of the pull-down unit. Operate VAG 1390 continuously. The choke valve should open to the second gap. Measure and adjust using a 2mm Allen key on the end of the pull-down unit's operating rod, both small and large units. 7. Remove VAG 1390 and replace the hoses. If a closely defined first and second stage movement is not obtained, or the choke valve keeps closing, replace the pull-down diaphragm unit. Note that in the hose between the engine and the green reservoir, there is a black and white one-way valve. The black side should face towards the green reservoir. Adjustment of the cold start enrichment tube. 1. Hold the choke valve fully closed. 2. On the choke valve with a hole, adjust the tube so that the bottom of the tube is just level with the upper edge of the hole. 3. On the choke valve without a hole, adjust the tube so that the bottom of the tube is 1mm above the closest surface of the choke valve. If the tube is too high, poor cold starting will result. If the tube is too low, an over-rich mixture will result, causing hunting and high fuel consumption. We've seen the operation of the choke assembly and the controls and adjustments necessary to obtain good starting and cold running characteristics. After the break, we'll go on to look at the idling system. Now stop the tape and refer to the workbook. Stage 2. Idling. The job of the idling system is to keep the engine running at a low speed using the minimum fuel and air. The 1B and 2B carburetors differ at idling from the theoretical carburetor shown in Carburation, the Basic Principles, in that the throttle valve is closed at idle and there are two idling systems. Because the throttle is closed at idle, air cannot pass into the engine via the throttle valve. Therefore, another method of passing air into the engine is used. That is, by an air bypass channel. Hence the commonly used term, air bypass carburetors. The closed throttle valve and the air bypass channel are the secrets of these carburetors. At idle, with the throttle closed, the airspeed through the bypass channel is extremely high. The speed creates a very strong depression within the channel, which is used to obtain a very accurately metered fuel-air mixture from the idling jets. Note that if the throttle valve is open at idle, or the engine has poor compression, the airspeed through the bypass channel will be slower, and the idling system will not operate correctly. The idling system is in two parts, the basic idling system and the auxiliary idling system. Let's take a look at the basic system first. The depression in the inlet manifold and the very fast airspeed through the bypass drilling act on this drilling. This causes the higher atmospheric pressure to force fuel through the main jet and into the basic idling fuel jet. At the same time, atmospheric pressure will force air through the basic idling air jet, which mixes with the fuel at this point. The fuel-air mixture flows through the drilling and is controlled by the CO adjusting screw before entering the engine in front of the cut-off valve. The basic system, as the word suggests, caters for the basic fuel-air supply for idling. But don't forget that it also supplies the progression drillings. Now the auxiliary system. The addition of the auxiliary system allows for very accurate fuel-air adjustments to be made. The very fast airspeed passing the end of this tube creates an even stronger depression at this point, allowing the atmospheric pressure to force fuel through the main jet into the auxiliary idling fuel jet. Air enters the auxiliary idling air jet and once again mixes with the fuel. The fuel-air preparation passes along the drilling and is controlled by the idling speed adjusting screw before entering the engine in front of the cut-off valve. The amount of fuel-air preparation flowing into the engine from the auxiliary system is dependent upon the strength of the depression acting on the auxiliary emulsion tube here. To slow the idle speed, the idle screw is moved in. The airspeed through the bypass drilling slows down and the depression weakens at the auxiliary emulsion tube. As a result, less fuel-air preparation flows from the auxiliary system, weakening it. If the screw is moved out, then the reverse takes place. The system is enriched and the idle speed is increased. Note that after adjusting the idle speed, CO may change and should be corrected using the CO screw. The final item in the idling system is the electromagnetic cut-off valve. When the ignition is switched on, this valve is energized and opens the idling bypass channel. On switching off the engine, this valve de-energizes and closes the idling bypass channel, stopping any fuel-air mixture and thus preventing running on. The 2B carburetor has an additional fixed non-adjustable basic idling system for the second stage. This ensures a more even distribution of idling fuel-air preparation into the engine. This is where the jet is located, and this is where the fuel-air preparation leaves the carburetor. Any corrections for CO are carried out on the first stage CO screw. Now for idling adjustments. Firstly, all prerequisites should have been checked and corrected. Then the idling adjustments can commence. 1. The engine should be up to operating temperature, 70 degrees C. 2. All current consumers should be switched off. 3. The crankcase breather hose should be off and plugged on the air cleaner side. 4. The engine throttle valve is closed. See the workshop manual for the method. 5. Connect the tachometer and CO meter. 6. Set the idle speed for the particular vehicle. 7. Set the CO for the vehicle. If, after adjusting the CO, the idle speed changes, repeat steps 6 and 7. 8. Reconnect the crankcase breather hose. The CO may rise. Do not readjust it. On these carburetors, then, we've seen that there are two idling systems to be considered. Having dealt with the adjustments of idling speed and CO, in the next section, we'll look at what happens during the moving off sequence. Stop the tape and refer to the workbook. Stage 3. Progression. The progression system is designed to provide extra fuel to ensure a smooth changeover from idle to main system. Without it, there would be a flat spot or hesitation during the moving off sequence. Once again, our two carburetors work in the same way for first stage progression. As the throttle valve opens, the air passing between it and the progression drillings creates a depression. This provides extra fuel air for a smooth changeover from the idling to the main system. The fuel air is provided by the basic system idling jets. Because the basic idling jets have to carry out two functions, that is, idling and progression, their fuel and air jet sizes are larger than the auxiliary. If, as is possible on certain carburetors, the basic and auxiliary jets were interchanged, the result would be difficulty in adjusting the idle speed and CO and flat spots when moving off. Flat spots and hesitations can also occur if the throttle valve is open when carrying out the idle and CO adjustments. The reason for this is progression fuel is used and gives a high CO reading, which is corrected by turning in the CO screw. This, in effect, allows the engine to idle on progression fuel, and when pulling away from standstill, there isn't enough progression fuel left for smooth acceleration. As far as adjustments are concerned for the progression system, there are none, other than making sure that the jets are in the correct position, that they are the correct size, and the throttle is closed at idle. So, the progression system on these carburetors is quite conventional, and there are no adjustments. After progression comes the acceleration stage, which we'll look at next. Stop the tape and refer to the workbook. Stage 4. Acceleration. Under moderate or hard acceleration, a metered amount of neat fuel is pumped into the airstream to assist in initial acceleration. The 1B and 2B both use a piston-type accelerator pump, which operates in the same way as the diaphragm type explained in Carburation, the Basic Principles. When the throttle is closed, the piston moves up, the pressure valve closes, and the suction valve opens, drawing fuel in to fill the space below the piston. When the throttle is opened, the piston is moved down and the suction valve closes. The piston pressurizes the fuel until the pressure valve opens and fuel for acceleration is forced into the airstream from the acceleration pump jet. The pressure valve has three functions. 1, it stops fuel running back. 2, it ensures a small pressure build-up to enable a clean spray without dribble. 3, it prevents a depression in the venturi from drawing fuel out of the jet. The 2B has an additional hollow weight in the body of the accelerator pump jet. When the throttle is opened quickly, it's forced up, restricting the flow. As the fuel pressure reduces, it drops down and full flow is restored to the jet. This prevents over-injection when both throttles are opened suddenly. Note that under or over-injection will cause flat spots or hesitations, which are quite often mistaken as progression flat spots. Therefore, correct injection quantities are essential. Both carburettors are adjustable either by removing the carburetor and catching fuel, or in situ by using VAG 1388. The 1B is adjustable by moving this cam, and the 2B by lengthening or shortening this rod. The spring on this rod plays an important part in the system too. When accelerating quickly, the piston will be subject to hydraulic locking. The spring gives to relieve the pressure and then expands to push the piston down smoothly. Also, at the end of the piston's travel, the spring acts as an override so that the throttle linkage can continue to move without jamming. The 1B carburetor has two versions of this spring. Firstly, this spring, which does the same job, or the second version on the throttle linkage as shown here. This spring is often too weak and causes acceleration delay. If this is experienced, unhook the spring, move it clockwise 2 or 3 notches to increase, and reclamp. Ensure that full movement of the quadrant is attainable. That's the accelerator pump then, and the adjustments. In the section after the break, we'll look at the control of cruising, the main system. Stop the tape and refer to the workbook. Stage 5, Main System. The main system controls continued acceleration and cruising. The 1B has one main system, whereas the 2B, being a two-stage carburetor, has two main systems. The main jet and air correction jet are matched to suit the particular engine to which the carburetor is to be fitted. The air correction jet is not removable. The 2B has one set in the first stage and another set, differing in size, in the second stage. Note that the first stage main jet is the smaller of the two. Interchanging the main jets will cause overall poor performance and high fuel consumption. There are no adjustments possible other than to ensure that the air correction jet is not restricted in any way. For example, not carboned up. Also, make sure that the main jets are in the correct position and the right size. Carboning up of the air correction jets or mismatching of the main jets will give either a weak or rich mixture for cruising, which will result in poor performance and or high fuel consumption. As the main system weakens the mixture, the full load enrichment system comes into operation, which is the subject of the next section. Stop the tape and refer to the workbook. Stage 6, Full Load Enrichment. Under full throttle and high engine speed, extra fuel is necessary to maintain the correct fuel-to-air ratio. Rather like the main system, the 1B has one full load enrichment tube, and the 2B can have one or two. If only one is fitted, it will be in the second stage, because, as explained in Carburation, the Basic Principles, the full load enrichment system only works at full throttle. And with a two-stage 2B, full throttle is only obtained when the second stage is wide open. Adjustments. First stage. The tube is adjusted as shown in the section on cold start enrichment earlier in the program. Second stage. There is no adjustment, but the tube should be checked for condition. It should be straight. If these tubes are too high, then a lack of top speed will result because of a weak mixture, and engine damage may occur. If the tubes are too low, then overfueling will take place, resulting in engine misfiring at high speeds and high fuel consumption. We've seen that either one or two enrichment tubes are used on these carburetors, and that the adjustments of these are crucial for good fuel consumption. In the next part of the programme, we'll look at the additional features of these carburettors. Stop the tape and refer to the workbook. Additional features. So far, we've looked at the 6 stages of carburation. Well, on the 1B and 2B carburettors, hidden away within the 6 stages, are 1 or 2 refinements. One of these refinements is to improve the cold idling of the engine by giving a slightly higher idling speed for 1 or 2 minutes longer after the choke is fully open. This is achieved by use of the disengaged choke valve linkage. Both the 1B and 2B have this device, but it's best explained using the 2B carburetor. It works like this. When cold, the choke valve closes and the linkage moves the fast idling cam onto the highest step. Constant contact between the choke valve and linkage is maintained by this spring, the disengagement spring. During the first 4 minutes of running, the choke's bimetallic spring relaxes and the choke valve moves to the fully open position. But the disengagement spring is still maintaining constant contact between the choke valve and the linkage. In this position, the fast idling cam holds the throttle valve slightly open on the last step of the cam. After a further 2 or 3 minutes, the disengagement spring is opened, which allows the linkage to move the fast idle cam away from the fast idle screw, fully closing the throttle. The movement is achieved by the use of a temperature-sensitive thermo spring. An owner could report that his throttle appears to stick after a fairly high-speed run. It's not the throttle sticking, but the thermo spring has been cooled down by the very fast airflow and has brought in the slightly increased idling speed. It normally returns to idle again after 1 or 2 miles of normal driving. There are no adjustments to the system to overcome this characteristic. The action of the thermo spring should be explained to the owner, and it should be made clear that there is nothing wrong with the carburetor. So this refinement of the choke assembly allows a faster idling speed for a longer period of time when the engine is cold. Stop the tape and refer to the workbook. Another refinement is second stage progression. This system gives a smooth integration of the second stage main system. Unlike the first stage, it does not work off the basic system, but has its own jets. The air jet is located here, and the fuel jet here. As the second stage throttle valve opens, the air passing between it and the progression drilling creates a depression, which allows the neat fuel already in the emulsion tube to flow into the engine, acting rather like acceleration enrichment. This is immediately followed by fuel and air being forced by atmospheric pressure through their respective jets to mix in the emulsion tube. This prevents overfueling as the throttle is opened further. When the second stage throttle valve is closed, the air bleed drilling prevents siphoning. The mixture on the left continues into the engine and on the right drops back to float level. This air bleed hole is very small and becomes blocked easily. The main cause is a dirty air filter being disturbed and then being replaced without blowing out the dust with an air line. To help prevent this, there is now a brass post in this position with the air bleed hole in the side. In the event that either of these versions becomes blocked, the vehicle will suffer erratic idling and difficult hot starting. This happens because the contents of the second stage float chamber will be siphoned into the inlet manifold during idling, continuing after the engine is switched off. Telltale signs that the air bleed has been or is blocked are small pools of fuel around the carburetor top. Second stage progression, then, is similar in its operation to first stage progression, but operates via separate jets. Stop the tape and refer to the workbook. The final refinement is that both carburetors are fitted with extra enrichment systems known as part throttle enrichment. Both are depression operated. The 1B via a diaphragm unit and the 2B via a piston and valve. To start with, let's take a look at the 1B diaphragm version. Firstly, there are two versions, one on the 1B1 fitted to LT vehicles and the other one on the 1B3 carburetor fitted to saloon vehicles. Both work in exactly the same way, but the fuel is directed to different areas of the carburetor. With the throttle closed, the depression below the valve acts on this drilling, which in turn pulls the diaphragm against the return spring until the O-ring on the end of the valve closes the hole from the float chamber. When the throttle valve is opened, the return spring overcomes the lessening depressions and moves the diaphragm back, opening the hole from the float chamber. At this point, the 1B1 and the 1B3 differ. Taking 1B3 first, when the throttle opening is at progression position, the depression here will allow fuel to flow from the open enrichment valve through a restrictor. This limits maximum fuel flow into the basic idling fuel-air jet, increasing the fuel-to-air ratio coming out of the progression drillings. When it operates in this way, it is called lower part throttle enrichment. With the 1B1 carburetor, the drillings in the carburetor top are different and direct the fuel into the air correction jet's emulsion tube, which increases the fuel-to-air ratio coming out of the main system's discharge arm. Therefore, the throttle has to be opened further before enrichment can take place. When it operates in this way, it is called upper part throttle enrichment. Lower part throttle enrichment, used on 1B3 carburetors for cars, is to improve the acceleration capabilities of the vehicle. Upper part throttle enrichment, as used on 1B1s fitted to LT vehicles, is to improve the cruising capabilities with heavy loads and wider throttle openings. The 2B's carburetor's enrichment system operates in the same way and for the same reason, but uses a piston and separate fuel enrichment valve instead of a one-piece diaphragm unit. Like the 1B1, operating in this way, it is called upper part throttle enrichment. There are no adjustments possible to the enrichment systems of the 1B or 2B carburetors. A faulty enrichment valve could be the result of a punctured diaphragm, a broken or removed O-ring, a piston sticking, a jammed enrichment valve. The symptoms that a faulty valve will give are uneven running with constant steady throttle between 30 to 50 miles per hour, poor idling with much increased CO strength, and high fuel consumption. The 1B diaphragm unit has been modified from this to this to prevent leakage and to stop the O-ring being pushed off the end of the shaft. It's recommended that when the diaphragm type enrichment valve is removed, that it is not reused but replaced by a new unit. This is because unless the carburetor is completely cold when the valve is removed, the valve will distort and thus leak. Part throttle enrichment operates in either the upper or lower throttle ranges and should be borne in mind when diagnosing carburetor faults in these areas. Stop the tape and refer to the workbook. Depression-operated second-stage throttle. Having looked at the refinements, there is one last area which we should investigate, and that is the operation of the depression-operated second-stage throttle of the 2B carburetor. Two versions have been used. The metal diaphragm housing and the black plastic unit both operate in the same way. When the first stage throttle is closed, the second stage throttle is prevented from opening by this mechanical locking cam. This cam releases the second stage throttle when the first stage throttle is approximately half open. The depression for operating the second stage diaphragm unit is created via two small drillings situated in both venturis. When the first stage is opened, the depression created in the venturi acts on the second stage diaphragm unit, opening the throttle only when the first stage mechanical lock releases. As the second stage opens, the depression created in the second venturi also acts on the diaphragm, increasing the depression to fully open the second stage throttle. When the throttle is closed, the first stage mechanical lock cam also closes the second stage. This is made possible by use of an override spring in the diaphragm unit's operating rod. Once the throttles are closed, the depression ceases and the diaphragm returns to its original position. Adjustments. There are no adjustments on the plastic diaphragm unit. The metal diaphragm unit should be checked for the operating rod length by releasing the ball joint and measuring the distance between the center of the ball and the base of the seat. It's adjusted by lengthening and shortening the operating rod. On certain vehicles, the 2B carburetor second stage is fitted with a thermo-pneumatic valve. This is to delay the opening of second stage whilst the engine is cold. This achieves two things. Firstly, it improves the cold progression characteristics of the engine, and secondly, it prevents maximum power output of the engine being used quickly until the engine reaches operating temperature, which prolongs engine life. As we've seen, the second stage throttle is linked to the first stage throttle not mechanically, but by a vacuum unit. This allows progressive operation of the second stage. Stop the tape and refer to the workbook. Summary. Any starting problem could be due to a choke fault, but don't assume that it is until all basic engine settings have been checked and, if necessary, adjusted. If the problem persists, check the following, with the engine cold, of course. That the choke closes, that it opens progressively over a period of 4 minutes as the engine warms up, that the choke assembly has the correct code number on it, that the pull-down diaphragm unit is in good condition, that the choke valve gaps are correctly set, and on vehicles with a cold start enrichment tube, that the tube is set at the correct height. Incidentally, on vehicles with a disengaged choke linkage, check that the throttle remains slightly open for a further 2 minutes. If there is a warm engine idling problem, then the idling system should be investigated. Make sure that the engine is warm, 70 degrees C, the choke is open, the throttle is fully closed. Check the throttle stop screw adjustment. Now, adjust the idle speed screw to achieve the correct engine speed. Adjust the CO screw to the correct value. If it's necessary to repeat the idle speed adjustment, always finish off with the CO screw. If it's difficult to obtain a smooth idle or the correct values, the cause will probably be either the basic idling jets, the auxiliary idling jets, or the throttle valve not closing. However, don't overlook the obvious. For example, an incorrect float level or a damaged needle valve. If the customer reports hesitation or flat spots during the initial moving off from standstill, you'll have to road test the vehicle and simulate the conditions described to you. Even better, have the customer demonstrate the symptoms to you. If the problem occurs with gentle acceleration, it is most likely to be in the progression system. Check the usual engine prerequisites, that the throttle is closing fully, that the correct idling fuel jet is fitted, that the progression drillings are not restricted. However, if the problem occurs with harder acceleration, whether from standstill or not, the accelerator pump should be investigated. Firstly, check the quantity of fuel being pumped. If it's greater than required, an adjustment will usually correct it. If the quantity is less than required, it could be an adjustment problem, or the accelerator pump piston sticking, the piston seal damaged, the suction valve remaining open, the accelerator pump jet restricted, the pressure valve dirty or sticking. And of course, don't forget the hollow weight in the pump jet on the 2B carburetors. If the owner is experiencing uneven running characteristics during continued acceleration and cruising, the following areas could be at fault: the main system, either the lower or the upper part throttle enrichment system, or on a 2-stage carburetor, second stage progression. Check that all the appropriate jets are the right size, fitted correctly, and are unrestricted, and that the enrichment valve is in good condition and functioning properly. Lack of top speed points to the full load enrichment system. Don't forget that road tests for this must be carried out at high engine revs. The height of the enrichment tubes is crucial for correct full load enrichment. If overall poor performance is experienced with the 2-stage carburetor, the fault could be a malfunctioning vacuum-operated second-stage throttle, caused by, for example, a punctured diaphragm, a broken operating rod, or a damaged vacuum hose. This is the end of the program. Further programs in this series will look in detail at the other types of carburetor fitted to VAG vehicles.